So today remember the plan was that we're going to focus on Wyngaard for the next couple weeks. There are five really important chapters that we're going to discuss each in turn, so that when we talk about the oceanic case as well, we'll have the equivalent of these different layers. So there's the atmospheric boundary layer, the atmospheric surface layer, the convective boundary layer, the stable boundary layer. We'll have a sense as to what those are like in the atmosphere. We'll also be able to go back and notice those in the ocean as well. So like we said last time, the atmospheric boundary layer is much better understood because that's where we live, and also it's transparent, so it's easier to observe. So there's a greater depth of understanding of how it works. But that being said, there's some differences between the atmosphere and the ocean, and so we're going to try and focus on the equation level today, and we'll start to see some of the differences and some of the similarities. Broadly speaking, the equations of motion are going to be extremely similar in the case of a dry atmosphere, a dry, shallow atmospheric boundary layer to our ocean boundary layer. But we will also briefly compare to the deeper atmospheric effects, and which involves more compressibility, and also the moisture equation. So that leads to clouds, etc., etc. That's part of the boundary layer as well. So we will touch on that part just a little bit, although it won't come. It'll play a role a bit when we discuss the convective boundary layer, but not so much in the surface layer. So we'll see how that goes as we go along. All right, so the plan today is to discuss the equations of atmospheric turbulence. And like I was saying before everybody got on, Wyngaard uses the index notation for tensors. So we were going to do a little bit of a refresher on a few of those equations as we go along. He actually prefers the physicist style notation, which is orientations number 1, 2, and 3 for the x direction, y direction, z direction. And so we'll also just think about how that goes on its own. Well, let me close this part, make it a little bigger. Okay. So, just like we did in the ocean, we're going to have a background state which will have potentially stratification in it, and then we'll have a foreground state which will have the turbulence in it. And just like in the oceanic case, we're going to talk, or in the Vallis case, the generic GFD case, we want to talk about the relevant approximate equations that might be used. For the background state, it's basically going to be relatively simple, in that it'll be the ideal gas equation for the equation of state. So that's given here as equation 8.1, which is just that the pressure goes like density times temperature with some constant. For the background state, we'll assume that it is based on a hydrostatic background, so that the pressure increasing in the x3 direction, that's the z direction, goes like rho g, which is, or minus rho g, just as we saw last time. So that basically is pressure decreasing with altitude. And then the one other piece of information we need in order to get the background state sorted is the a thermodynamic equation. And so in this case, the thermodynamic equation is going to be the second law of thermodynamics, which is the conservation of entropy equation. And here we don't have a dissipation of entropy term, but we have the entropy goes like the enthalpy and then a pressure variation. So where H is the specific enthalpy and then Cp is the specific heat per unit mass. We can do a little bit simpler than this by adding a few, by exploring the second law of thermodynamics a little better. So if we say that the entropy is actually conserved, like this, which means that we're considering isentropic motion is the motion that makes up the background state. That means that following a fluid partial that's going up and down in this background state, it conserves its entropy. It has its it is an isentrope. Then we get the other two terms in that second law of thermodynamics balancing each other, this one and this one. So we get an equation that looks like this, which basically says the enthalpy goes like 1 over rho times the pressure. If we plug in, we can combine the hydrostatic and the isentropic rule together. So dp naught dx3 gives us dp naught dx3 there. And then the isentrope, the only direction in which it's varying, if it is a background motionless state, is in the x3 direction. So this equation becomes this equation if we're considering the background profiles that only vary in the z direction. Then if we plug in with our definition for the background temperature related to the background enthalpy, that gets rid of this side and turns it into a temperature equation. And then using this isentropic relationship, we can convert from we can also convert into an enthalpy units, and so what we find is that the temperature in the z direction decreases at a constant rate in this background, with the rate given by gravity over the specific heat per unit mass at a constant pressure, Cp. And if you plug in the numbers for this using a dry atmospheric conditions for Cp, we find that it's about 1 degree Kelvin per 100 meters height. So that's what we would expect the background decrease to be as we go up. That's about that's the decay rate that this implies. Okay, so that's the background state, but what about the turbulence that's superimposed on the background state? So there's a little bit of slightly confusing notation that Wyngaard uses, but I actually have come to like it over time. Where he uses a tilde to indicate the total field, that is the background plus a perturbation like this. This part is a turbulence only component. This part is the total, so you can put the two together. So for pressure, he's got the background pressure plus the turbulent perturbation pressure is the total pressure. The temperature is the background temperature plus the turbulent perturbation. The density is the background plus the turbulent perturbation. And now we'd like to write out equations, governing equations, so that we can solve for either the tilde part or the prime part. Doesn't really matter which we solve it for, they would be equivalent. But that's what we need, is we need to now close this set of equations. We know what the background state is for the dry atmosphere anyway, which is just that temperature decay rate, and then the equivalent, the corresponding pressure and density fields that go with it. So what about the perturbation field? So in general, the density in a dry atmosphere is going to depend on the temperature and the pressure, which we could linearize into being a temperature-dependent part and a pressure-dependent part. So this is like a linear equation of state for the atmosphere, similar to the linear equation of state for the ocean that we talked about, where this is the alpha and this is the gamma, the density change with respect to pressure. And similar to how we talked about in the ocean, if the motion is much slower than the speed of sound, then this second term is actually not very important. And the first, so if for low Mach number flows, the first term is the more important one. So basically the perturbation density goes with a scale factor that depends only on the background state, but is still potentially a function of z, depending on what background state you have. And then a temperature prime. So anomalies in density are anomalies in temperature. That's the key. The conservation of mass equation is exactly the same as the conservation of mass equation we described in Vallis. So there's the flux form, where we have the flux of mass versus the rate of change at a particular location, the tendency of density. Or we could write it as a material derivative plus the density times a divergence. And I'm going to show in a second on the board why that's the divergence. Let's do that right now. Okay, so switching over to the board. So the key in these index notations, I hope everyone can see clearly, is when you have a repeated index like this, two i's, it means you should interpret that as the sum over I from 1 to 3 of d by dxi, rho twiddle, ui twiddle, or d by dx, rho u twiddle twiddle x, plus d by dy, rho u y, or sometimes we call that v, plus d by dz, rho u z, or w. So you can see, oops, I need my twiddles. So hiding inside of this repeated index is both a summation symbol, and if we think about what the summation symbol is, it expands out into multiple terms. So if I were instead to write d by dxj, rho twiddle ui, this would be just one particular combination, because you have to tell me what j is and what I is. But this is called the Einstein summation convention, which Einstein realized, smart guy that he was, that this, writing this extra symbol of the sum only occurs when you have repeated indices. And so as a shorthand for that, you just suppress that summation symbol and just look at the indices to see whether they're repeated or not. And if they are repeated, then you get the sum over all three directions. So that's the way the Einstein summation symbol works. I hope everybody's seen that before. That's a little bit quick. We're going to come back to that in a second because we want to look at the Coriolis term, which is a bit disorienting. But the other way of writing this was to write it as the material derivative plus rho twiddle du twiddle I dxi, oops, I don't want to twiddle on that one, equals 0. And so this is the mass conservation in the flux form, this is the material derivative form, and this is the one that we're always focusing on. We're normally thinking about material derivatives going, but this is like a Boussinesq system. It's actually an anelastic system because our density profiles have some z dependence, so they're not totally constant. But we can still evaluate the importance of this term. So how important is that term? Well, it's, this and suppresses, since I have an I in both the upstairs and the downstairs, it's a summation over I. So what does that mean? That means du dx plus dv dy plus dw dz. That's what this is. So that's just the density times the divergence, which is the way we're used to seeing it from Vallis. So how big is that divergence is the next question. So let's go back to the slides. Let me make sure that I was broadcasting in. Yeah. So how big is that divergence? Well, if we think about it just for the background part of the flow, it's really the vertical velocity component times the rate of change of density in the vertical direction. That's the important part. And you could think of that instead, noticing that there's a rho naught here and a rho naught there, you could think of that as just the vertical velocity divided by some height over which the density is varying. If you go back to our definition of which is this, and if you go back to the definition using the ideal gas law of what we had for the background density, we see that this is just the scale height for the density. I mean, you can also get that from right here. This is the, if you move the rho naught to that side, look, that's just an ordinary differential equation for rho naught in the z direction, and it would be an exponential because it has a rho on both sides. So this is the decay scale of density with height from that exponential solution, which we talked about in class already from Vallis, which is somewhere between 7 and 10 kilometers. And so on the order of 10 kilometers, this would be a negligible deviation from incompressibility if the vertical scale of the motions were much, much smaller than that scale height. So how big do we expect the vertical scale of the motions to be? Well, in the troposphere, the troposphere is somewhere between 10 and 30 kilometers, depending on where you are. That actually would be an order 1 variation, and so we would want to worry about this extra piece of compressibility. But we're going to see that in the atmospheric boundary layer, where we're really focused on 3-dimensional turbulence, not synoptic turbulence or mesoscale turbulence, the whole depth of the boundary layer is order of a kilometer. So it's about 1/10 of the scale height. So if it's only 1/10 of the scale height, that means that this divergence of the 3D velocity, at least for the background component, is going to be a relatively small, kind of 10% of this other term. So we might frequently be able to neglect this deviation term and just focus on the material derivative of density, or think about it this way as well. So, putting these pieces together, we have a conservation that looks like incompressibility, which is going to be true if we have a L less than H that's in the scale height, the vertical deviation is less than the scale height. That looks really familiar. That looks a lot like our Boussinesq or Anelastic equations. In fact, it is the Boussinesq or Anelastic equations. We have a Navier-Stokes momentum equation. So let's look at that, the terms in that. So here's the tendency of momentum in the I direction. Here is the material derivative term. And notice now how the I here matches the I here. So whereas the J matches the J means you sum over J. So that's U dot grad is that UJ dd xj. That's U dot grad. And then UI, this I comes out because it is not repeated. So this object is a vector. This object of dui dxj is actually a second-rank tensor with both I and j components. But when you dot it into uj, it goes back to being a vector, which is in the I direction, the same as this first term. So the other thing about the indicial notation is that if you're adding together two things, they need to have the same indices. You can't add a vector to a vector that's in a different direction, or a vector to a scalar, or a vector to a second-rank tensor, or anything like that. You need to match. Each term has to have the same exposed, that is unsummed index, and any other indices that appear in the terms need to be summed over. That's an important part of the rules for how to make each term in the equation covariant. So now when we come over to this side and we look at the pressure gradient term, we see that it also has only one index, which is also the I direction. So this and this have the same index character. 1 over rho tilde, d pressure tilde. So this is the full Navier-Stokes momentum equation. This has the full density and the full pressure still in it with the nonlinearity implied there. And then here's the gravitational acceleration, also in the I direction. Here's what is the Coriolis term, which is a bit hard to recognize in this form. I'm going to come back to that on the board in a second. And then here's the viscosity. So we've made a few assumptions here that you might, for those of you who are paying attention to the tensors, might have been thinking about. One, we're not making any distinction between lower indices and upper indices. So effectively, we're assuming that this is a Cartesian coordinate system for I and j, which is a fair assumption because our horizontal deviations are not going to be a large fraction of the radius of the Earth. So the curvature of the Earth is totally suppressed here. A local Cartesian coordinate system is fine. And in fact, what we're doing here is it's really a tangent plane approximation, just like we saw in Vallis. We haven't really specified what direction the rotation is pointed. Why is that not going away? We haven't specified what direction this omega is pointing. And this funny Levi-Civita symbol, epsilon I j k, omega j u k, we need to explore that a little bit more to figure out what's going on with that. So, but this is the generic fluid dynamics for a rotating stratification coming here through rho tilde, Navier-Stokes, because the friction term is still present. This is the Cartesian coordinate system way of writing that. Okay, let's think a little bit more about what 2 epsilon I j k omega j looks like. Oops. Go over the back of the board. Okay, 2 epsilon I j k omega j u twiddle k. All right, so what is this thing? Remember our Coriolis term. This does not include the centrifugal term, but this is our Coriolis term. What was it in Vallis? It was 2 omega cross u, written that way, where omega is the rotation axis of the Earth, the whole Earth, I guess, and we're considering a tangent plane somewhere else. So there are a couple of things that are worth, so maybe here's our little boundary over there with its local coordinate system. 3, x3, x2, x1. Did I do it right? 1, 2, 3. Yeah. Okay. So 2 omega cross u is, here's the omega, is in that direction. What direction is u in? It could be in any one of the 3 directions there to write 2 omega cross u. But this object is a pseudo vector, right? This is the Coriolis force, and well, it's a pseudo vector if omega and u were vectors, but actually omega is also a pseudo vector, so it's a vector. So this is the Coriolis force, or Coriolis acceleration is probably a little bit clearer because it doesn't have density in it. How is that related to this? So we need to understand better what the epsilon I j k symbol is. So epsilon I j k is the Levi-Civita totally antisymmetric tensor, which has the property that it is 1 if I equals 1, j equals 2, k equals 3. It's 0 if any of the 2 indices are equal to each other. If I equals j, or j equals k, or I equals k. And it's -1 if you swap any index from this original 1, 2, 3 configuration. So that means epsilon I j k equals minus epsilon j I k equals minus epsilon k j I, etc. So let's write out some of the ones that are +1. So epsilon 1, 2, 3, 1 is equal to that, but it's also equal to epsilon 2, 3, 1, which is also equal to epsilon 3, 1, 2, and minus 1 is equal to epsilon 2, 1, 3, which is equal to epsilon 3, 2, 1, which is equal to epsilon, what's the other one? 1, 3, 2. So you can see that one of the things, it stays the same if you cyclically rotate the indices. So 1, 2, 3, move the 1 over to the other side, 2, 3, 1 equals 3, 1, 2. So these are the positive ones. Here are the negative ones, 2, 1, 3, 3, 2, 1, 1, 3, 2. And again, you can see they're cyclic permutations of each other. And then all the other ones are 0. So 0 if it's epsilon 1, 1, 2, etc. Okay. So how does that end up being the cross product? Well, let's go back and look at this guy a little bit more. So what are we summing over here? We're summing over J, we're summing over K. And so this has only one index that's exposed, it's I. So in the same sense as this has one vector direction, this has one vector direction left over, the I. And the J and the K are summed over. And do we know that this is perpendicular to omega J? Well, we can imagine summing it into the omega J direction, omega J, or omega I, times 2 epsilon I J K, omega J, U twiddle K. And so this one is summed over I and summed over J, but that has to be equal to minus the 1 J I K omega I U twiddle K. So I just flipped one of the indices in the Levi-Chiva symbol, which gives us minus the opposite one. But now look, I have an omega here, which is on J, and an omega here, which is on I, but I could switch those around. This is just multiplication. There's no ordering that's important in these kind of index notations. So I could write this one here, 2 epsilon J I K, epsilon I, U twiddle K. And now I have omega J. So there's J's, there's I's, and then there's K's. But it doesn't matter what label I put on these indices. I'm summing over all the J's, I'm summing over all the I's. So I could just as well swap out the I's for J's and the J's for I's, like this. I make every J into an I, and I make every I into a J. And now look what we've just shown. We've shown that this is equal to its opposite, this. And something that's equal to its opposite is equal to 0. So we've just proven that if we dot this funny operator into omega, it's 0. So just like this was, if I dotted the Coriolis force into omega, I would get 0. If I dotted the Coriolis force into U, I would get 0. That game goes almost exactly the same way if I dotted this into U. So indeed, this object is perpendicular to omega, perpendicular to U. It is a tensor, it is a first rank tensor because the I is the only exposed piece. It's proportional to omega, it's proportional to U, therefore it's the same as the original Coriolis force, just written out in a different way. So hopefully that's been a little bit helpful for those of you who are struggling with the vector notation stuff. That's a little bit of a reminder about how those arguments go. So in general, if we want to write a cross product of two vectors, we can always write it as the Levi-Chiva symbol I, J, K U, J, V, K. And the amazing thing about this is that unlike the div grad and curl notation that's not with the indices, this actually preserves the ordering of derivatives. If I wanted to take the curl, I can do it the same way. I just make sure that the derivatives are to the left of the thing that I'm operating on. And so now I can read this as the partial derivative of v in this direction. This takes care of all the indices, the Levi-Civita part, and as long as I'm careful about swapping the order of the derivatives, I get all of those vector calculus relations are easy to derive for free. All of the triple product curls, everything like that come out of this epsilon ijk. And one of the most useful formulas in all those derivations, which I hope everybody, is this funny thing. This is called the Epsilon-Delta Relation. And it basically says if I contract two Levi-Civitas together on this index, this one, and you can also, of course, permute either one of these and do all the minus signs because we know the properties of Levi-Civita symbols. This thing actually becomes a double Kronecker delta. So Kronecker delta, this is equal to 1 if these are equal to each other, it's equal to 0 if they're not equal to each other. And so look at what this does. Here is one index from the first one and one index from the second one. One index from the first one, one index from the second one. That's these two. And in this sequence is where they're in the same order there. And then minus the other one. So this is the one where you have I from here and M from here and J from here and L from there. Oops, sorry, they're the same orientation. And that one comes in with a minus sign. So you can take this one relationship and prove all of the triple products of the curl and the back cab rules and all of that come neatly out of this relationship. And if you're curious about where this comes from, you should just sit down and start writing out some of the components and convince yourself that that's the way it has to be. And you can see that if I switch I and J here, that's what this term is, which means that they are the anti-symmetry of I and J here is preserved on this side, but it's across these two terms. And similarly, in the anti-symmetry here of L and M is here across those two terms. Okay. Oh my God. Sorry, so I said all that and didn't record it very well. I hope you guys were watching the right screen, but I managed to blow it on my screen recording and not cover any of that on the screen recording. Oh well. Are there any questions about any of that before we move on? Let me see. The chat box is going. Lots of questions. Okay. Galen asked a while ago what justifies the conservation of entropy. This is basically an assumption about the kinds of motion that would form a background. The motion is sufficiently quasi-static as to not upset the entropy. So we talk about this in the ocean from the perspective of thinking about the potential temperature for a vertical convection. And that's equivalent through the ideal-Cass law to the conservation of entropy. It's actually not the best. Oh yeah, sorry about the video resolution. Yeah, sorry, that's another issue. You should have a receive video resolution setting that's underneath your setup, and if you set that to high definition, you actually can read what's on the whiteboard. Sorry, I should have said that before. So back to the conservation of entropy. So if we had slow vertical motion, you can imagine that if it wasn't really turbulent, it would actually kind of, that parcel would just compress or expand under the changing pressure as it went up and down, but it wouldn't change its entropy. For turbulent motions, that's actually not a very good approximation. And so there have been a lot of recent developments on this. One of the interesting things about the enthalpy is that the enthalpy, even when you're in the presence of turbulent mixing, can be conserved. So it's way beyond what we're going to talk about here today, or even in this class, but you can do possibly a better job of thermodynamics for a dry atmosphere or a zero salinity ocean that does using something called conservative temperature, which uses the free energy rather than the Gibbs free energy rather than the conservation of entropy, which allows you to have finite mixing but still keep track of what the background profiles look like. It's a relatively small contribution, and it really is only important for very deep convection that it makes a big difference for the background. So that's what we'll have for that. We're not going to be talking too much about deep convection in either the atmosphere or the ocean. So we're focused more on the boundary layers where those distinctions are not too big.
Okay, so just to make sure I got that, so the main idea is just that the background variation, you're just using that basically to define the background variation as small.
Yes, and it turns out that you do a kind of similar thing for the entropy of the turbulent motion too, which basically says that it conserves potential temperature defined like this. So both of them are assumed to be isentropic motions in this particular idealization. It's actually not as clean when we get to the moist equations, which we're going to write down in just a second. Because then there's a conversion between moisture and temperature from latent heat. Okay, but so we've done a bunch of stuff going back and forth between the vector equations. So we have the mass equation. Oh, I didn't do the anelastic equation yet. So the next thing that we might worry about from this Navier-Stokes is, well, there's this nonlinear term here in the pressure gradient force. But if we introduce our background variation and our perturbation for the pressure and keep only the lowest order contribution, then we find an anelastic form for this, which is that this guy, the division by this, depends only on the background part, and the pressure gradient depends only on the turbulent part, not the background pressure, and in exchange for that, we end up with this funny multiplier on the gravity. So the gravity is measured in units of temperature anomaly over background temperature. And if we look at that thing, it looks a little bit like buoyancy. And in fact, it is the buoyancy. We're going to see that in a second. So here's the anelastic version of the momentum equation. Everything else is the same as in the Navier-Stokes except for the pressure gradient term and the now buoyancy term instead of the gravitational acceleration. And the last thing we need to worry about is the conservation of tracers. If we have a flux law for tracers, so if there was a density of a tracer, it would have this kind of a flux law with the potential of a diffusion of that tracer. And in the atmosphere, it's convenient. So we could also write this with a material derivative, just like this. So that's just doing the expansion of this derivative out on these two and collecting together the material derivative part and the divergence part. In the atmosphere, they frequently like to think of the ratio of two densities. So the density of one conserved tracer versus the total density of the fluid. That's called the mixing ratio. And it has units of mass per mass. So what mass of tracer versus the total mass, rather than this density, which is the mass of tracer versus volume, or the regular density, which is the mass versus volume. And the mixing ratio always has a material derivative form that looks like this. So it's a material derivative equals a diffusivity approximately, There's a funny rho-rho correlation here that normally gets dropped because it's relatively small normally. Okay, so here are the equations of motion for the dry atmosphere then. We have the anelastic momentum equation, and we don't make any assumptions about whether the Coriolis, the axis of rotation of the Coriolis, is in the vertical or not. We don't have to make that assumption here. The buoyancy is acting in the vertical because the G is acting in the vertical. So delta 3(1) means that it's only acts in the vertical direction. It's the potential temperature here that is the buoyancy part. So deviations in potential temperature are what lead to ascending and descending air force accelerations in that direction. Because of the relatively shallow vertical scale versus the scale height, we can use incompressibility as a good approximation. The potential temperature satisfies a material derivative kind of advection equation with a diffusivity. There's one other funny term here which looks a little unfamiliar, but this is a heating term based on the divergence of radiation. So if sunlight is coming in and getting absorbed, then there's a divergence of the sunlight, and that is actually leads to heating, so leads to changing the entropy or changing the potential temperature of the fluid at that location where the radiation is diverging. So this is another term that we haven't talked about. It's true also in the ocean, but this term is only important right near the surface where the light can penetrate. And then the last thing is that if we had any tracers and they had a mixing ratio C, it would have an equation like this. So we can compare this set of equations versus Vallis' set of equations and make some nice correspondences. So here, this is the non-rotating form of Vallis' momentum equation. But you can see here's the material derivative of a momentum. That's the same. Here is the pressure anomaly scaled by the background density, which is the same definition as the geopotential in the Vallis' version. Here is the buoyancy as written for the atmosphere in this ideal gas configuration, and here's the buoyancy here. It's delta 3I, so it's only buoyancy k hat. And here is the Coriolis term, which we just talked about in any direction. So Vallis doesn't write the Coriolis term here. But one of the nice things about writing it this way in tensors is we don't have to assume that F is vertical or anything, or omega is vertical. It is the full one without the traditional approximation here. And then there's a viscosity here, which Vallis has chosen not to write, but that would be the same in between this equation set and this equation set. Here's the incompressibility, here's the incompressibility, here's the buoyancy equation, here's the potential temperature equation. So the B dot here could be either coming from the diffusion or it could be coming from the divergence of radiation. Both are non-conservative, non-materially conservative contributions to the potential temperature. And the potential temperature here through this relationship is what's driving the buoyancy. And then finally, any other tracer you might have would have a material derivative equals a diffusivity, and that's in fact the form that we have for either temperature or salinity in the oceanic form. So on first glance, pretty much all of the important details come through. And so even though we've used this tensor notation and this tilde and prime notation, it's actually very similar to the equations we already discussed in Vallis. So if we go to a moist atmosphere, and this is not including rainfall, this way of writing the equations, I just wanted to show this briefly. I'm not sure how much we're going to discuss this form of the equations, but if you contrast the dry equations versus the moist equations, the key distinction you see is you have a new definition of potential temperature. So it's a potential temperature that has the background potential temperature plus some other correction that has to do with the amount of relative, the specific humidity. So the specific humidity is a mixing ratio for the density of vapor versus the total density. So we need that mixing ratio equation to tell us how this Q tilde evolves, and here it is. There's the mixing ratio equation for Q tilde. So the specific humidity is materially conserved plus a diffusivity, and we now see that there is a buoyancy effect. Buoyancy is going with the V form, the vapor, including vapor form, which includes both the regular old potential temperature plus also this nonlinear multiplier of the specific humidity and the potential temperature. So the key is when you have moisture, you might have more buoyancy than you expected due to the presence of the specific humidity. So this set of equations is a little different. And so moist air rises at a different rate than dry air. The equations are slightly different, but in some broad sense, like if the turbulence terms we're really interested in are things like the Reynolds stresses that comes from this term, or the temperature fluxes that comes from this term. Those are not so different as they were before. You just have to keep track of two species in the atmosphere. The same way as in the ocean, we had to keep track of salinity and temperature. Now you have to keep track of potential temperature and also specific humidity. And I just wrote in a couple of definitions to make everything totally clear where all these pieces are coming from. And really, the specific humidity, the reason why it's coming in is because it's a change in the density for the equivalent temperature. That's basically what you're getting, because you're changing the density of the air as you go. All right. So, unfortunately, or maybe fortunately, I don't know, these equations are too complicated to solve directly. We know we can't solve them because we have specific molecular diffusivity, molecular viscosity here as written like this. So instead what we need are Reynolds average equations. And so Wyngaard uses the ensemble averaged equations. And the reason why ensemble mean is a good one is because it commutes with all of the derivatives. So if you take the time derivative of the ensemble mean, it's equal to the ensemble mean of the time derivative. If you take the spatial derivative of the ensemble mean, it's equal to the ensemble mean of the spatial derivative. That means that it's really easy to write out mean equations. So then now we're taking our U tilde and writing it as a mean part. That's the ensemble mean. So over many instances of the turbulence, this U would be the common velocity. This is the perturbation that's specific to each turbulence instance. Similarly, for the pressure field, there's a mean pressure, and then there's a specific instance turbulent pressure, temperature, and it's the vapor, potential temperature, etc. All these pieces go through. You play the same game that we normally play, and you see, oh, look, here's the material derivative of the mean, affected by the mean, and here's the pressure field, and it's still Boussinesq, or still Anelastic, and here is the Coriolis Force acting on the mean, and then here's the buoyancy, and it's acting on the mean, and so lots of commonalities with what we saw before, except look, here's a covariance of the turbulent component that is appearing. So this is the Reynolds stresses appearing in the mean equations. Similarly, the temperature equation, the mean temperature equation looks like that, except now there's a turbulence flux that appears in the temperature equation. And here, again, for the mean equation, here is a turbulent tracer flux that appears in the temperature equation. So this is a lot of what we talked about when we were talking about how to think about both the turbulent and diffusive stresses in the oceanic case. And we could put in, say, an eddy viscosity to replace this term, or an eddy diffusivity to replace this term, or an eddy diffusivity on the on the other tracers to replace this term. But instead, Wyngaard goes through a different set of calculations, which is, what if you actually knew the fluctuations? If you had a turbulent equation, how could you find this cross correlation? So what if you knew the whole flow, or were able to use a large eddy simulation to estimate these terms, at least at the largest scales? What could you do? And you can write subgrid equations through this process. So if you want to write the time derivative of of the covariance of two turbulent equations, because it's an ensemble average, you can move the derivative inside, and then you can do just the regular old product rule on those different contributions. So if I had an equation for B and I had an equation for A, I could multiply the equation for B times A and multiply the equation for A times B, add those together, and get an equation for the covariance of A and B. This process means you can derive fluctuation equations for all of the turbulence quantities that are needed for the mean equations. They won't be closed because in the B equation there will also be covariances, and in the A equation there will also be covariances, and so you'll get triple products here. But you can at least go one more step in the derivation. So, for example, here's an equation of motion for the Reynolds stresses. Here's the Reynolds stress tensor. Reynolds stresses are advected by the mean. There is this, which is the production of Reynolds stresses by the mean shear. And here's a different term, which is also a production of Reynolds stresses by the mean. And look at these two. They're funny. So J goes to J, and K is hanging, and I is hanging. And then this one, J goes to J, and I is hanging, and K is hanging. But look, these two are symmetrized. This is K and I that way, and this is K and I the other way. So when you add those together, you're making something that's symmetric in I and K. And look, the original equation is symmetric in I and K. So these are the shear production terms, they're called. They're producing Reynolds stresses from mean shear. There's a turbulent transport. There's the triple product. This is the one that you can't close for. You need a new equation for the triple product, which is the turbulence closure problem. Here's the pressure gradient interaction, or sometimes this is called the pressure strain term. Here's the Coriolis term written out. And look, it has a really interesting vector component. It's got M's and K's and M's and I's in a special way to keep it symmetrized for these. And then the dissipation is, now we see epsilon is really playing a role. This is where we said the strain rate tensor comes in. And in fact, the strain rate tensor is really there in this equation for the Reynolds stresses. And because this is symmetric in I and K, this is also symmetric in I and K. Okay. And you could do the same thing for tracer fluxes. You could do the same thing for variance equations like the tracer variance, which is written out here. So that's all I wanted to talk about today. And sorry, we've used more time than we thought reviewing tensor stuff. Were there any other questions about the homework? I guess I'll say, so A and B are just something that we have equations for. You can always write that equation out. So this is responding to Akash's question. You can always write out those covariance equations if you know the equation for A and you know the equation for B. You might not actually have all of the terms in that equation, but this is a way of determining what things you might want to measure if you want to think about the production of the covariance of A and B. So it would be very typical, for example, to have all the terms in that equation except for the triple product term. And if you don't have the triple product term, you can't actually close that budget, but you might still know that measuring the turbulent dissipation would be important, and measuring the buoyant production would be important, measuring the Coriolis term in this way would be important, measuring the pressure gradient interaction like this would be important, measuring the shear production terms would be important. So this is really that very simplified equation that we saw in Thorpe, where he said that it was shear production plus buoyancy production minus dissipation is kind of a volume average of this turbulent Reynolds stress generation equation. This is a pointwise set of equations to think about how they're generated. Okay, so I'm going to upload the key for the homeworks, and hopefully everybody can take a look at the other ones that they're assigned to do for peer review by Thursday. And I haven't uploaded the full key yet because I want to write the first two equations out, the first two problems out, the ones on Ekman. They're a bit ugly if you do them the way that's recommended, so I want to write them a little bit clearer before I post those two answers. But all the other answers from 3 to 8 are posted already, and or I think they should be, or I will post them momentarily. And and I will start giving you feedback on the projects, on the project abstracts as soon as possible, so that people get moving on the project. And the other thing that's important is, I sent out an email, but I'll just remind you all that we canceled homework number 6. So we just have one more homework problem set. That's going to be on the chapters from Wyngaard. And so I'll post that today as well. And then the remaining assignment will be the project. And that will be drawn from a lot of the papers that we're discussing. As people go and independently, you'll look at different papers and different pieces of that. And so that's kind of when we have reached the research level, is when we're done with the Wyngaard reading. Any other questions? All right, thanks everybody. I hope you're doing well and staying safe. I'll post the video later today, and we'll see you soon. And I'll give you feedback on projects over the next couple days. All right.
Thanks, man.
Bye-bye.